In the first semester of calculus, one of the things you talk about is constructing the tangent line. Since you need to know the slope of that line, there was an argument by which you look at the function value at the spot you're interested in, you look at it at a nearby spot, and construct the straight line that passes through those 2 points. You can easily calculate the slope of that. Although it's seldom mentioned, this implies that I can calculate f at all x values that are close enough to c, and that when I calculate this difference, when I take the limit as the delta x tends to 0, these secant lines eventually turn into the tangent line. I want to look at this from a slightly different point of view, though. This fraction for a given delta x number is typically not the value of f prime of c. As delta x becomes very small, though, it gets close to f prime at c. Another way that I could think about this is this. There's a number, L, which is secretly f prime evaluated at c, so that when I calculate one of these fractions, the answer that I get is exactly L plus the difference between this and that. The epsilon tends to 0 as delta x tends to 0. This is logically equivalent to the usual definition. Rearranging this, another way that I can say f is differentiable at x equals c is if the actual difference in the function value is exactly equal to some fixed particular number times delta x plus epsilon times delta x, where epsilon tends to 0 as delta x tends to 0. The L is, again, secretly f prime at c. The reason that I bring this up at this point is this is going to indicate what I ought to do in order to define a function of more than one independent variable as being differentiable at a spot. Using yet another notation for the derivative, I could write it this way, and people have invented some abbreviations to help out here. Since the function value in this case is a y-coordinate, this difference is going to be called capital delta y, the actual change in the y-coordinate on the graph of the function. Being slightly sloppy with the notation, I write dy dx without specifying that this is an actual number. It is the derivative of f evaluated at x equals c. We'll just understand that. At some point, someone had this idea. Dy dx is not a fraction. It's not dy divided by dx, but in many cases it acts as though it was, for instance in the chain rule. So some clever person decided that not only am I no longer mentioning where I'm evaluating this derivative at, I'm going to let delta x have two names. One of them is delta x, and the other one is dx. This is terrible notation. This is not a fraction, and that dx is not a number. But that one is. Awful notation. And finally, in the most awful notation of all, take this thing which is not dy divided by dx and multiply it by this thing which is really secretly delta x, except we're calling it dx also. It certainly looks like a fraction multiplied by the bottom of the fraction. So this quantity is given an abbreviation. We call it dy. So what I mean by a function being differentiable at x equals c can be written this way. It is necessary that delta y equals dy plus some number epsilon times delta x, with the proviso that the epsilon has to go to 0 as delta x tends to 0. At first glance, this looks like I'm taking an idea that was relatively easy to understand and unnecessarily complicating it. It is slightly more complicated looking, but these kind of ideas will extend to functions of several variables in the way that the original idea did not. In Calc 1, if I ask you what does it mean for a function to be differentiable at x equals c, there's an easy answer. It has a derivative at x equals c, which again has the hidden assumption that the function makes sense at x equals c and any place sufficiently close. Life is not so easy when I've got more than one independent variable. What we'll do is we'll think, as we did in this new formulation, my function values are actually going to be z coordinates on the graph. X and y are independent variables. Changing x will induce a change in the function value. Doing the same for y will induce some other change. And thinking about how we said things were going to go, the following, which is kind of complicated, is the most reasonable looking definition that people have been able to come up with. We are going to say that f is differentiable at the point ab if the actual difference in function values starting at some point ab and ending at some point a plus delta x, b plus delta y can be written this way. It's the rate at which f is changing with respect to x only at the spot we started at, times how much I changed the x. There will be another contribution, though, the rate at which f is changing when I change y only, times the amount that I changed the y variable. As before, typically we don't expect an exact equality, but we expect the agreement between this and this sum to become better as the delta x and delta y go to 0. So I'll think of having error terms epsilon 1 delta x plus epsilon 2 delta y, where the epsilon 1 and epsilon 2 both go to 0 as delta x and delta y both go to 0. If I had more than two independent variables, I would just add more partial derivatives times change in the variable, and I would have more epsilons. Working directly with the definition is extremely tedious. Very soon we'll have a way to tell in many cases whether or not a function is differentiable without going through the tedious pain of the definition, but I feel like we should do at least one. So I want to show that this function, f of x and y equals x squared y cubed, is differentiable at all points by using this definition that we've got. I'm going to have to calculate two things. I'm going to have to calculate delta z. I've got to calculate dz, and then see if somehow I can't express delta z as dz plus something that tends to 0 times delta x plus something else that tends to 0 times delta y. Calculating dz turns out to be the easy part. The partial derivative of f with respect to x is 2xy cubed here, and partial of f with respect to y of this function is x squared times 3 times y squared, which I think looks nicer if I write it as 3x squared y squared. These partial derivatives must be evaluated for x equal a and y equal b, so substituting those values in, this is my formula for dz. If I write out what f evaluated at a plus delta x and b plus delta y are, it is the square of the first number times the cube of the second one. When I subtract away f at ab, I'm going to get a squared times b cubed, whatever those numbers are. I have to convince myself somehow that this difference is the same thing as dz plus two terms that act in the appropriate manner. This isn't going to be difficult at all. It's just going to be tedious because of the amount of algebra that you have to do. I quickly got the coefficients for the b plus delta y cubed bit from Pascal's triangle. So what I'm going to have to do is to take this and multiply it by that, and then subtract away a squared b cubed. The strategy that I'm going to follow is basically the FOIL method. I'm going to take each one of these terms and multiply them by each one of these terms, and then add everything up. So there's nothing hard about this. It's just a lengthy calculation. Usually when we do something like this in Calc 1, lots of things cancel out, and it's good news. The good news here is extremely limited. The a squared times b cubed terms cancel out, but nothing else does. It's worth noting, though, that in what's left, you have constants, the 3's and the 6's and so on. The a and the b are the coordinates of the point that I'm thinking about. I'm thinking of those as not moving around at the moment. Everything else is a factor of delta x or delta y, or a power of delta x times a power of delta y. I'm going to group similar things together. Everything that has a single delta x, I will group together. Everything that has a single delta y, I'll group together as well. And then I've got to think about the rest of it. Scanning through, there's something that has a single delta x in it. Not looking at that one, it has delta x times delta y in it. Not looking at that one, or that one, or that one, or that one, or that one. In this formula for delta z, if I'm looking for something whose dependence on delta x and delta y is that it's just got a delta x to the first power in it, there is only one of those, and it's right there. Then I'm going to scan through this formula looking for terms whose delta x or delta y dependence is that it just has one delta y in it and no delta x's. There's one. No, no. Looking for delta y here. Got two factors, delta x and delta y. Got two delta y's. Got three delta y's. That doesn't have any delta y in it. That has a delta y, but it also has two factors of delta x. That has more than one factor of delta y. and so does that one. So if I'm looking for something that is a constant times delta y, there's only one term that looks like that. In everything else, there's either more factors of delta x than just one, or more factors of delta y than just one, or at least one factor of delta x and one factor of delta y. What I'm going to do with these remaining horrific-looking collection of terms is I'm going to group them together into two pairs. In each sum that I'm going to group together, on the one hand, there's going to be at least a delta x in each term, and when I factor that delta x out, whatever's left will still go to 0, as delta x and delta y go to 0. The second chunk, I'll do the same, except I'll make sure that after I factor a delta y out, everything that's left inside goes to 0. If I can do that, then this will show me what the epsilon 1 and the epsilon 2 should be. So we've already canceled out the a squared times b cubed. We've already written down here 2 times a b cubed delta x. So this term has been accounted for. I've written down 3a squared b squared delta y, so that term has been accounted for. And then all of these other terms, I'm going to put them in one sum or another that I have already factored a delta x out or a delta y, and I want to make sure that each term that remains inside of either one of these sums has at least one factor of delta x or delta y. This term, 3a squared b delta y squared, if I factor a delta y out of that, I'll have 3a squared b delta y. I had to put that term in the second one because it didn't have any factors of delta x in it. So that's been accounted for. Plus a squared delta y cubed, if I factor a delta y out of that, I'll have a times delta y squared left. Both of these terms will tend to 0 as delta x and delta y tend to 0. So that one. A squared, that is, although that won't make any difference. That's been accounted for. I have 6ab squared delta x delta y. This term has both factors of delta x and delta y in them. I could put this in either one of my sums. I'll put it in the first one so that the second bracket doesn't fill up so quickly. So that one's been accounted for. And continuing in this manner, I find out that I can write delta z as these two terms plus something times delta x plus something times delta y. The first something, each term has at least one factor of delta x or delta y in them. As delta x and delta y tend to 0, the quantity inside the first parentheses tends to 0 as well. As delta x and delta y tend to 0, the same happens inside the second parentheses. And lastly, what about this quantity up here? When we calculated dz, it was 2ab cubed delta x plus 3a squared b squared delta y. Two ab cubed delta x plus 3a squared b squared delta y. Those first two terms actually form dz. So we have literally argued, regardless of what the point AB is, for this function, delta z is exactly equal to dz plus epsilon 1 delta x, this would be the epsilon 1, plus epsilon 2 delta y, this is the epsilon 2, and the epsilon 1 and epsilon 2 tend to 0 as delta x and delta y goes to 0. We have proven by the definition that the function we started with is differentiable at every point. Obviously, we don't want to be doing a great deal of this. It turns out that if the first order partial derivatives are continuous in a region that contains the point of interest, then the function is automatically differentiable. I'm going to think of moving from the point AB to the point a plus delta x, b plus delta y in two steps. Firstly, I'll change only the x variable, and after I figure out what's going on here, I'll change the y variable. In this way, I can use ordinary one-variable calculus and everything that I know about it. I could either think of this as the mean value theorem or Taylor's theorem with remainder. F evaluated at a plus delta x, b plus delta y is exactly the value of f at the b equals y value plus the rate of change of f with respect to y evaluated someplace times delta y. The beta is between b and b plus delta y. On the other hand, I'm going to think of this now as being a function of x only. I'm going to start in my mind the x at a and change the x to a plus delta x and apply the same idea. F at a plus delta x, b plus delta y is the function value at ab plus the partial derivative of f with respect to x evaluated at x equal alpha, y equal b times delta x plus the term that we had before. In this case, alpha is some number that's between a and a plus delta x, as beta is between b and b plus delta y. This tells me that delta z, the actual change in function value, is exactly this quantity for some number alpha between a and a plus delta x, and some number beta between b and b plus delta y. This strongly resembles dz, but is not dz, because we are not evaluating the derivatives at ab. To get this into the correct form, I need to have these partial derivatives evaluated at AB rather than these other points. I'll just do an algebra trick here. If I were to multiply this out and then combine it with this term, the f sub x ab delta x would cancel out, leaving behind f sub x alpha b delta x, which is what I actually have, and likewise if you multiply this out and add it to this term, you recover what we had before. So this is just a sneaky way of writing these things. So the upshot of all of this is delta z is dz plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 is this quantity and epsilon 2 is this quantity. This is the point at which the continuity of the partial derivatives comes into the picture. If I assume that both of these first-order partial derivatives are continuous, then as delta x and delta y tend to 0, alpha, which is between a and a plus delta x, must approach a. If the partial derivative is continuous, then its limit is going to equal the partial derivative of f with respect to x evaluated at ab, and that's what I'm subtracting away. So as delta x and delta y tend to 0, in particular, epsilon 1 tends to 0. Likewise, as delta x and delta y tend to 0, a plus delta x tends to a, beta, which is between b and b plus delta y, must approach b. If the partial derivative with respect to y is continuous, the limit of this quantity is the partial of f with respect to y at ab, which is what I'm subtracting away. So not only do I know that I can write the delta z in this format, I can also tell you that as delta x and delta y tend to 0, the epsilon 1 and epsilon 2 tend to 0, and that's the definition of the function being differentiable there. This is a polynomial function. Its partial derivatives are easy to calculate. The partial derivatives themselves are polynomials, and polynomials are continuous every place, so this fact tells me that my original function is differentiable every place. We don't even really need to do any work on this one. This is a rational function. It's continuous every place except on the line y equal x. If we were to do the quotient rule to either find the partial with respect to x or partial with respect to y, there would be a polynomial upstairs and a square of x minus y downstairs. That tells me this function is differentiable every place except on the line y equal x, where it doesn't even make any sense. For introductory purposes, people often look at problems like this. I'm going to calculate the kinetic energy of some object, but I've got a problem. No measurement process is perfect. If I measure the mass as being 10 kilograms, there is inevitably some uncertainty about that. So I'll think of a situation where the measured mass is 10, but I acknowledge that I could be off by as much as 0.3 of a kilogram, either overestimating or underestimating. The speed will be 20 meters per second, but again, I had to measure that, and I'll say, in this case, I might be as much as 0.1 meter per second low or high. When we do differentials, the names of the variables mean nothing to us. We've been using z for the thing that we're estimating, but now I'll just use e. The names of the variables usually have been x and y, but now they'll be m and v. Since I expect my measurements to have errors in them, it's a reasonable question to ask, how much does the energy change if I change the mass a little bit, if I've measured the mass incorrectly, and therefore I'm not quite using the right value? Likewise, if there was a mistake in the velocity. The actual change in energy will be approximated by the differential, which is the partial derivative of whatever it is I'm talking about with respect to the first variable, times how much I changed the first variable, plus the rate of change of energy in this case with respect to the second variable, times how much I change the second variable. For my mass, I'll use the measured value 10. For the speed, I'll use the measured value 20. And the dm and dv are how off I may be in my measurements of mass and velocity. This is where some books use a rather odd notation, which I'm going to avoid. All I'm going to say about delta m, it could be as big as 0.3, it could be as small as negative 0.3, or anything in between. Delta v is going to be no more than 0.1 and no further to the negative side than negative 0.1. I don't know if delta m and delta v have the same sign or opposite signs. If they've got the same sign, these two terms will tend to reinforce each other. If they have opposite signs, then they'll be a partly canceled quantity. I'm going to use the triangle inequality in a minute to get rid of this ambiguity. It's a total coincidence that these numbers both work out to be 200. I'm going to take 200 times some number that's between negative 0.3 and 0.3. I'm going to multiply 200 by some other number that's between negative 0.1 and 0.1. I'm going to add those two things together, and this is going to give me an estimate of how much the energy could change. I don't know if delta m is positive or negative, likewise for delta v. If I want to prepare for the worst case scenario, I'll think about what happens if they both have the same sign. The absolute value of the change in energy is no bigger than the absolute of this plus the absolute of that. 200's a positive constant, so I can pull that out. The absolute value of delta m is no more than 0.3, and absolute delta v is no more than 0.1. So the change in energy has an absolute value which is no bigger than 200 times 0.4, which is 80 joules, if I'm using kilograms and meters per second. Any reasonable person might be thinking, is that a lot? It depends on how big E is. So using my m equal 10 and v equal 20 numbers, let's calculate what the energy would be. The energy works out to be 2,000 joules, so 80 isn't a huge number compared to the actual value of the energy. A similar situation is sometimes seen where the uncertainties are given as percentages instead of specific values. Let's take a look at one of those. Suppose I have a quantity J that depends on two variables named Q and T, the relationship given as J equals Q divided by T squared. We measure Q as being 4, but we could be off as much as 3%. We measure T as being 6. That could be off by as much as 5%. Calculating the differential is no problem, But what is a problem is I don't have actual numbers for delta Q and delta T, so we'll have to do something about that. Knowing that Q could be off as much as 3% means that the uncertainty in Q, the delta Q, divided by Q, can't be any more than 3%, 3 parts per 100, which would be 0.03. Likewise, delta T divided by T can't be any bigger in absolute value than 0.05. That's 5%. So I'm going to try to think of the relative uncertainty in J. So I can actually write the differential of J divided by J as some combination of delta Q over Q and delta T over T. Once more, I don't know if one of these quantities is positive and the other is negative, or if they're both positive or if they're both negative. It's possible, for instance, that this could be positive and that delta T over T might be negative. So even though there's a minus sign there, the terms would reinforce each other. It's also possible that this number is positive and 2 times delta T over T is positive as well, in which case there'll be a partial cancellation. If I want to prepare for the worst case scenario, I can tell you that the absolute value of dj over j is certainly no more than the absolute value of delta q over q plus twice the absolute value of delta t over t. So putting in the upper bounds for how big these two absolute values can be, I find out that the uncertainty in J is no more than 13%. I hope everyone's having a good day. I'll talk to you again soon.